Today we're diving into two breakthroughs that could redefine how computers work. Not just faster, but fundamentally different. And the secret lies in physics. What if the computers of the future didn't get hot, didn't waste energy, and instead ran on light and exotic quantum particles called excitons? Today we're taking a peek into the future computers that could be just beyond the horizon, and some interesting implications. Let's dive in. I'm Ben. This is Physics or Bust. Modern computers are powered by electrons flowing through billions of transistors on silicon chips. But there's a problem. Electrons bump into things. They scatter, they generate resistance, and resistance generates heat. That heat is wasted heat. Right now, about 30 to 40% of the power in big data centers is spent just keeping computers cool. And for your laptop or phone, overheating is what throttles performance and kills batteries. If we want to keep advancing, we need a way to compute without all that wasted heat. That's where excitons and photons come in. We'll dig into the physics in a minute, but first, if you like this video, you'd probably like this book. I've got a link in the description below. I do get a small commission, but it wouldn't cost you any extra. So what exactly makes an excitonic switch different from just letting electrons flow? Normally, when you run current through a semiconductor, you apply a voltage, electrons accelerate, and they bump into atoms. That scattering generates resistance, and resistance means heat. That's the bottleneck. But an exciton works differently. When a semiconductor is hit by light, or a precise voltage pulse, an electron absorbs that energy and jumps up to the conduction band, a higher energy state. That leaves behind a hole in the lower energy band, the valence band. The hole behaves like a positively charged particle. Now, instead of letting that electron wander off, researchers design the materials so the electron and hole stay bound together by Coulomb attraction. This bond state is the exciton, and it behaves like a tiny atom trapped inside the crystal. Here's why it matters. Excitons carry energy and information, but not net charge. They can move through the semiconductor like a wave without dragging electrons through resistive paths. In other words, they transmit signals without producing waste heat. But how do you make a switch out of this? The answer is nanoscale engineering. Scientists use 2D semiconductor materials, only a few atoms thick. Things like molybdenum disulfide or tungsten diselenide. These materials let excitons live much longer than in thicker crystals, long enough to move across the device. By applying tiny electric fields or shining controlled light pulses, you can decide whether excitons are created and allowed to propagate, or forced to recombine. That's your on-off mechanism. Off state, no excitons, no signal passes. On state, excitons form, travel, and carry the signal forward. This isn't just theory, though. A recent demonstration produced an excitonic switch about 100 times smaller than today's transistors. And since excitons don't produce resistive heating, the efficiency gains are enormous. In short, instead of simply freeing electrons and letting them bang around in a lattice, excitonic devices encode information in electron-hole pairs, turning the quantum properties of matter into practical computing logic. Now let's turn to the second breakthrough, computing directly with photons. In a normal computer, electrons flip bits between 0 and 1. But photons aren't just particles. They're also waves. And wave physics gives us new tools for computation. An analog optical computer uses beams of light and carefully engineered optical elements to perform operations. Instead of digital logic switches, it uses the physics of interference and diffraction. Here's the key. When two light waves overlap, they interfere constructively, producing a bright spot, or destructively, producing a dark spot. That interference pattern is literally math in action. Overlapping waves perform an operation equivalent to matrix multiplication, the backbone of modern AI and image processing. Think of it like this. In digital electronics, we simulate these interactions step by step with billions of calculations. In an optical computer, the wave physics does the calculation for free as the light passes through the device. The prototype from Microsoft and Cambridge combines three main parts. Micro-LED arrays encode input data as patterns of light. Optical lenses and diffraction structures transform those patterns of light, letting interference perform the actual computation. Photodetectors read out the output and convert it back into digital data. The result is computation at the speed of light. with almost no heat. For tasks like MRI reconstruction or optimization problems, the system has already shown up to 100 times higher efficiency than digital systems. And here's the physics beauty. Instead of using billions of transistor switches to simulate math, you let the law of optics themselves carry out the math in parallel. It's like outsourcing the heavy lifting to nature itself. Both of these breakthroughs, excitonic switches and optical computers, are tackling the same bottleneck, efficiency. Excitons reduce heat by replacing electrical current with neutral electron hole pairs, while also reducing size. Photons bypass resistance altogether by using interference and diffraction to compute. If either of these technologies scales, the impact is enormous. Data centers that consume a fraction of today's electricity, smaller personal devices that run cooler, longer, and faster, and entirely new computing architectures that break free from the slowing pace of Moore's law. These aren't just engineering tricks. They're deep applications of quantum physics and optics, using the very building blocks of the universe to push beyond the limits of silicon. Now, we've gotten devices pretty small recently, but if we can have transistors that are 100 times smaller while running cooler, there are a lot of possibilities for what can be done with future computers. We've already seen companies putting computers in glasses that look eerily similar to the original Mission Impossible movie. Just imagine the spy tech that could be created with excitonic microchips, AI-enabled drones that could actually be mistaken for flies or bees, pen-sized computers with the same computing abilities as your phone, or pocket computer, as I sometimes call it. If you thought we were getting computers small now, just wait till exciton microchips hit the market. So the next time your laptop or phone overheats, remember, physicists are building a future where heat isn't the enemy. A future where computers run cool and efficient, powered by excitons and photons. If you enjoyed diving into the physics behind future computers, remember to like and subscribe, and remember, keep asking questions. See you in the next video.